Hello! So today we're going to talk about vectors, and this is good because vectors are my favourite topic actually. I think they're super fun. Interestingly, a lot of people find them quite hard, and I think the reason is because it's very easy to just not have a clue what's going on. So we're going to really focus on trying to build the intuition for what vectors are and how they work. Okay, I'm sure this is obvious to you. This is a lighthouse on some rocks, and this is kind of the sea. And on the sea there might be some boats, so we're going to be like the Coast Guard or something I think today. And here's a little sailing boat. I want to know, okay, starting from the origin being the lighthouse, where is the sailing boat? This is just coordinates, right? Let's suppose it's 5 kilometers to the west and 3 kilometers to the north. So x coordinate 5, y coordinate 3. This is a vector. How great is that, right? You already know all about vectors anyway. It's a coordinate is a vector. It's called a position vector. So here is an example of a position vector. It's 5, 3, and all that means is it's a position that is 5 across the x-axis and 3 up the y-axis. Okay, I'm still the Coast Guard in my lighthouse. Let's suppose there's also like a ferry. Ferries are fun. It's like a bigger boat. Here we go. This is why I'm not an art teacher. This is my ferry. It's got like a chimney. There we go. Okay, so we've got a ferry, right? We've got a big old ferry thing and a sailing boat. Now, let's say the ferry is currently at position vector 2, 4. Okay? Now, that might be fine. We kind of also, as well as the position vectors of where the boats are now, we need to know where they're going. So for example, if the ferry in 10 minutes time is going to do this, that might be a problem. So we need to ask the ferry, what is your direction of travel and how fast are you going? In other words, what is your velocity is the posh word. And this arrow here, what this arrow is doing is it's going from 2, 4 to 5, 3. This arrow is going across 3 and then down 1. So this arrow we could represent by the column vector or component vector of across 3 and down 1. So here's an example of a component form of a vector. Okay, 3 to the right and down 1. In other words, it's like as if it was going across 3, x at the top, and going up the y-axis at the bottom. Okay, so going up -1 is obviously the same as going down 1. So this vector here, this arrow, what it is and does is it goes across 3 and down 1. Great, okay. That means as a Coast Guard I maybe want to tell my sailing boat and say, hey guys, could you just like go that way a bit and then you won't get squashed? So, I don't know, what does that look like? Let's say it's across 1 and up 2. So that basis vector, I could explain to them the instructions. I could say, please go to the right, I suppose that's west, by 1 kilometre and north by 2 kilometres. Now, that's a long sentence. It's kind of annoying. So as a mathematician, I'd like an efficient way of writing that. And here's what it is. Okay, we're going to just encode this to the right using like the letter I. So when I say I mean please go right 1. And this going north, this going up, I'm going to use the letter J for that. So when I say to J, what I mean to say is go north 2, please. So a basis vector, an example of a basis vector, could be to say I plus 2j. That means go right 1 and then up 2. Okay? So what we often do is, well, we often underline the vectors. So I and j, we're going to underline their vectors. So you could say this, let's call this vector v. Vector v, you know it's a vector because I've underlined it, because they're really cool, so we're going to underline them. Okay. Another example of a basis vector, let's suppose it's 3i minus 4j. underline my vectors. What does this mean? Pause and have a guess. Hopefully you think it means go right 3, 3 along the x-axis, and then go down 4, so 4 down the y-axis. Great, okay, so that's the concept of these different things. What we're going to do slightly is explore 3D coordinates, think about how far or how long a vector is, and then we'll also just talk about the concept of vectors being equal. Okay, so 3D vectors. Let's have a look at what we've got so far. This tells me where the boat is. It tells me, well, this tells me where the boat is. It tells me that it's at 5, 3. This tells me what the boat is doing. It says it's going right 3 and down 1. Let's suppose that I'm kind of adding a dimension. I'm going to be an air traffic controller now. Okay, no more Coast Guard, air traffic controller. Like, it kind of doesn't matter if the planes are on top of each other. Here's a plane. The planes can be on top of each other. That's fine, so long as the other one is like way up above it in the sky. So it doesn't matter if the planes are kind of flying past each other, but so long as one of them is way higher than the other one. Now we have x and y coordinates for like the spot on the land that their planes are on top of. We also need a z coordinate for like how high up in the sky the plane is. Okay, so what we're going to do is have some 3D coordinate examples. As a position, I might be at 5, 3, 10. Maybe that means that I am 100 meters above this fishing boat. I'm at the same x coordinate and y coordinate as the fishing boat, but I'm straight up above it. I'm a helicopter in the sky that's 10 units above it. Okay. Obviously, you can do that with the other forms of vectors. So my plane or my helicopter, I need to tell it how far up and down in the sky to go, as well as just how far left and right. So, for example, I might have a helicopter, and I might be, right, helicopter, I would like you to go 3 units right or west, 1 unit south or down, and also vertically, I want you to climb up in the sky so you'll get 5 units higher. Okay, so this instruction here says go right 3, down 1, and then vertically up 5. Okay, and of course I could convert this. I could write it in basis vector form. We would write 3i as a code for please go right by 3, minus j as a code for please go kind of horizontally down the y-axis by 1, and then, oh, what do you reckon, guys? Yeah, 5k, k just meaning please go vertically up 5. Okay, 5 units vertically up on the z-axis. Excellent. So now, as I promised you, we're going to think about how far these instructions are, how far I have to go to comply with that instruction, and we're going to think about what happens when 2 vectors are equal. So, next topic, magnitude. Magnitude, okay, that means how big. It's the same thing as a length. And this is easy, right? We've done this before. Check it out. Here's a vector. It goes 3 units right and 1 unit down. How long is that vector? I can do my Pythagoras on this vector here. Okay, 3 units right, 1 unit down. Pythagoras says that the magnitude of this vector, okay, what I'm going to do is write it like this. These lines either side mean magnitude or length or size. So the size of this vector is the square root of 3 squared plus minus 1, in brackets, squared, which is the square root of 9 plus 1, which is the square root of 10. How nice. So the magnitude just means the length, how far, and we can do it by Pythagoras. If we're in 3D, life is even more fun, right? So the magnitude of this vector, let's call this is h, isn't it? So the magnitude of h is the square root of 3 squared plus minus 1 squared plus 5 squared, which is the square root of 9 plus 1 plus 25, which is the square root of 35. Lovely number. I would leave it like that. Okay, so magnitude means length. You can do it by Pythagoras, which is basically you square up all of the lengths directions, add them, and then square root the answer. Okay? How you work out the magnitude or length of a vector. It works if there's just 2 parts in the vector. It works if it's a 3D vector or coordinate as well. Great. Final section. Loving this. Okay, what happens when 2 vectors are equal? What does that mean? So, first example, 3, 5. Next example, 3 minus 5. Are these 2 vectors equal? No. Go right 3 and north 5 is different to go right 3 and south 5. Okay, these are different, not equal. Okay, what does it mean for 2 vectors to be equal? Well, basically, the instructions both have to be the same. The same x right left instruction, the same y up down instruction, and the same z instruction as well, if we've got 3 dimensions. So, for example, let's suppose, I mean, this is classic, like just a bit of random maths with no reason behind it whatsoever. But let's suppose I have 2 vectors. One looks like this, 2a, 5f. So a and f are just numbers. And let's suppose I know, for some weird reason, that this random vector is actually equivalent, is the same as this instruction. Go right 6 and then go up 4a minus 2. So if I know that this is true, what does that mean? Let's do an implication sign. This fact here means that 2a has to be the same as 6. The go right instruction has to be the same. And also 5f has to be the same as 4a minus 2. The go up instruction has to be the same. And of course from here, I can say that if 2a is 6, a is probably going to be 3. And then from here, I can substitute that in there. It's like simultaneous equations now. How cool is that, right? Okay, 5f is now 4 lots of 3 minus 2. 5f is going to be 12 minus 2. 5f is going to be 10. That means f is going to be 2. So I can work out what these random unknown quantities are because I know that these two are equal. And what it means for 2 vectors to be equal is that the instructions, all of the instructions, especially like suppose there's another instruction, say it's minus 4 there, that would also have to be minus 4. They would have to be the same. All of the instructions would have to match. So I can get these 2 equations here from that fact and solve them simultaneously. Great. Love a bit of vectors.